typical nutrition the person has, the skin type. Particular diseases also are affecting peripheral blood flow. This is all affecting it. So what we need to build, and that's our grand, I would say, plan for upcoming 10 to 15 years, is to build our global human biophoton atlas, as we call it.
Welcome to the QBC podcast, where we explore exciting new paradigms that have a meaningful impact on our day-to-day lives. I'm your host, Meredith Oke. Let's keep the conversation going. Join us in our free community by visiting qbcpod.com. That's qbcpod.com. And let's see where the quantum superhighway takes us next. It is just so wild what our bodies do when you really start digging into health through the lens of light. And our guest today, we go super deep into biophoton emissions. What are biophoton emissions? Well, our bodies are emitting light. I don't mean that as a metaphor. I mean, literally, there is light coming out of our cells. And I don't mean like our body heat that would be picked up by like night vision goggles. I mean, photons, like actual light, or as it has now been renamed, biological autoluminescence. So my guest today is Michal Cifra. He runs a lab in Prague that is deep into the weeds studying biological autoluminescence. Stay through the podcast. He gives a big announcement about how all of you, yes, all of you, can participate in this biophotonic research. It is his dream to democratize it, which of course lines up perfectly with the mission at the Institute of Applied Quantum Biology to start sourcing data from the field, from actual practitioners who are out there in the weeds, putting all the research together in real life with real people, and all the beautiful mess that entails, and all of the gold wisdom and information that is buried in all of your practices, all of your visits to your clinician, health coach, integrative physician. So I think the future is finding ways to pull data from those interactions. And Michal Cifra has a really, really crazy cool project that he's looking to launch that he will tell us about partway through the episode. So stay tuned for that. He is, just a little background, an electromagnetic biophysicist and team leader of the Bioelectrodynamics research team at the Institute of Photonics and Electronics of the Czech Academy of Sciences in Prague. His earliest mentor was someone that the light nerds probably have heard of, and that was Professor Fitzalbert Popp. Was one of his early undergrad mentors, and his thesis advisor was none other than Roland van Wyk. So Michal is deep into the absolute latest research of our body's ability to create and give off light. It's crazy, crazy, fun, cool stuff, and I know you're going to love it. And if you want to get certified in applying these principles, and there will be principles of biophotonic emissions to be applied in clinical practice very soon. Keep listening. Do go to qbcpod.com and click on Institute and fill out the application and set up a clarity call. We'd love to have you in there. It is a no-pressure program. We have tons of support, tons of references, self-paced, plus live Q&As with faculty members for an ongoing period of time, as long as you want. As long as you stay a member of the QBC community, you're actually inside of there from the moment that you register. And even after you get certified, you can stay inside and access everything, including the calls. We want this community to be as cohesive and growth-oriented and research-oriented as possible. So come on in, jump in, go to qbcpod.com and click on Institute. Okay, and also visit our friends at bondcharge.com. We want to take care of our biology. As Professor Cifra talks about, there are biophotonic ways to tell when our bodies are out of balance and stressed and aging badly. It's also cool. So take care of yourself now with some of the amazing tools at bondcharge.com. And make sure you engage with your light by downloading the My Circadian app. Practitioners, there's a practitioner bundle. You're going to want to go order that. And then when you sign up a new client, they automatically get access to the app. You give them one of your codes that you buy in the bundle, and then they have something real and tangible to play with. They have the lux meter, they have the sunset times, the sunrise times, the vitamin D calculator, like all the fun stuff that will make circadian regulation a real thing for them, and probably a little bit fun because it's a fun app to use. Okay, everybody, thank you for being here. You are a joy to be around, and enjoy my conversation with Professor Cifra. All right, Michal Cifra, welcome to the Quantum Biology Collective podcast. So looking forward to this conversation. All right, so we're going to talk about a really interesting, fun topic today that our audience is familiar with, but not deeply. And I'd love to get into it, which is biophotonic emissions. So before you sort of explain like what that is, could you give us a little background about what you do and how you ended up in this very cutting edge field?
Absolutely. Thanks, first of all. Thank you very much for inviting me to speak about, this topic, which is, I would say, the closest to my heart, scientific heart. It's actually the research of human photon emission or biophoton emission is the thing which got me to the science in the first place. So I can tell you a bit of the actually personal story, which is exactly about how I got to the research of this topic. I was reading certain journals which are more about the philosophy, a bit of spirituality when I was undergrad student in the university, and I was studying biomedical engineering. I was always wondering how I can build, understand new technologies and devices, how to help the people, especially with any health issues potentially or preventing them. And in the journal, I read about, it was kind of popular story about the fact that the human body emits light. And I say, wow, that's weird. How is that possible, right? Because nobody told me that about the university and biomedical engineering courses. So I decided to explore it myself. So I arranged a contact with Professor Fritz Albert Popp, who is one of the founders of the photon field. And I arranged them to meet at a conference, and I just took him for lunch. It was a bit of not busy. And I said, hey, I would like to explore this more. So how can we do that? And he was a very generous person. I can say later on, I have a lot of, let's say, different opinions than he had on this field of research, but he was always a very generous person. And invited me to come to this International Institute of Biophysics, as they call it in Neuss in Western Germany. And I calculated there my internship, which I had in Germany, because I studied originally in Slovakia, in my home country. And there, suddenly, I find myself surrounded by the people like probably you, and who are very enthusiastic, going definitely beyond the edge of what is standard science, I would say. And they were all very interested to understand this phenomena. So this is how I go to the science there, and I slept there in a dark room, measuring how I shine during the night over the time, and it was my master thesis. And it was a lot of fun, and I still like to make this fun research, and I learned a lot over it's almost 20 years now. So currently I'm a team leader of the bioelectrodynamics research team at the Institute of Photonics and Electronics of the Czech Academy of Sciences. And we are exploring fundamental understanding of the field biomatter interaction. So how external fields affect the biology on a molecular and cellular level, especially, and how active biomaterials, organisms generate their field. So that's what we do in our research.
I love that you're looking at how the environment affects our biology, because that's, I think, something that is becoming more and more important to people. We've focused so much on our food and our fitness and our supplements and our prescriptions, but then we don't necessarily think about where in the world we're putting our biology and what is around us that is affecting it. Is that sort of what your team is looking to understand partially?
We are trying to understand how we call it, physical mechanisms of these interactions. So
Okay.
In broader research field of what you kind of called bioelectromagnetics, that's the research field or scientific field, which exactly deals with the questions how electromagnetic fields affect biology from the smallest scale, from the molecules to the ecosystems. So that's bioelectromagnetics. By the way, I'm privileged to be on a communication committee of the Bioem Society. However, this is not my role today, just to put it apart.
Yes.
So I'm
But
close
there
to the
is a
community.
wonderful conference for if anyone wants to dive into that. We'll put the link to that in the show notes as well.
So there, indeed, people are, since the time humankind started to use technologies using electromagnetism, electricity, so we've been exposed since already 100 years to the increasing degree of electromagnetic waves, microwaves, which we all use for wireless communication and other purposes. People are really interested to what extent this can be affecting the whole. I would say the consensus in the community, based on nearly tens of the thousands of studies, is that it indeed can be considered extremely mild stressor, but to the same level as drinking too much coffee. For example, radio frequency radiation is categorized as possibly carcinogenic, but this is all well-known public. But in the same level, in the same category, is just same as the coffee. So drinking too much coffee, for example, I like the coffee, by the way. I have nothing against coffee itself, as I have nothing against the wireless communication if it's done properly. So yeah, so this is to put it to the proper level. So it's categorized as something possibly carcinogenic because there are some studies which show that. However, everything can be carcinogenic if you just do too much of it.
Right.
And the public health levels are set to protect us against, vast majority of potential risks. So yeah, this is the consensus of the community, consensus of the bioelectromagnetic community. Of course, you can find some researchers, I would say it's one of the 100 who will tell you that this is not enough. You should be protecting more and other stuff. But I'm personally more how I perceive the, let's say, risk of being exposed by the external electromagnetic technologies is somewhere on a level that is just one of the myriads of the stressors we are exposed to. And this happens to be generated by the humans. It's not a natural stressor.
Okay. So you're talking about like Wi-Fi radiation, cell towers, things like that. So in your opinion, it is affecting our biology, but not to the level that we should be deeply concerned.
Yes, I mean this is I would say not only my opinion. This is I would say this is my opinion as well, but it's opinion of the vast majority of the scientists. I would say this is consensus in the bioelectromagnetics community. But I can say what can be much more harmful is actually believing is doing something wrong to you. The effect of nocebo, opposite of placebo, is extremely strong, and this is well known and proved. So for people who believe electromagnetic radiation is doing some harm for them, they could physically get harmed while not even being exposed because they believe it's something out there. So the psychology is extremely powerful and has to be carefully, I would say, separated. And it's very difficult in studies from actual physical effects of electromagnetic fields or any other, say, subtle fields.
I fully agree. Yes, that the psychological fear, the constant worry, panic is definitely going to have a detrimental effect, and potentially more of a detrimental effect than the actual electromagnetic fields themselves.
That's that in some, I would say, population, this is actually a real risk, I would say. And it's actually happening, I would say.
Yes, that's true. I mean, we all definitely, I would say, take a slightly more cautious view of the harms that could possibly be caused. However, not to the point of freaking out. It's sort of like we turn our Wi-Fi off at night when we go to bed, and I think most people would choose not to live next to a cell tower if they could avoid it, but it's not an overriding panic.
Yeah, I think it's a reasonable approach, of course.
Okay.
Of course, if I may add just a bit of it, of course, that science is always open, right? So with best of our understanding of this topic, we can say that we are safely protected. However, we never know what will be there in the long run. And it's any knowledge, right? So
yeah,
scientific knowledge might change, but it's very unlikely it will be dramatic change to a huge accumulation of knowledge which you have so far, at least in this level of the let's say protection of the population against unwanted effects of electromagnetic field. So there are some small probabilities something very dramatic would happen, I would say, which would completely overturn our understanding, but it seems to be unlikely based on the the tens of the thousands of the studies we've been with researchers all over the world in the last 60 years been looking into that.
I mean, there are people who take a different view, and there are also, I think, people who are more affected than others. Like you could have 20 people be fine, but one person gets knocked out by the same level, which to my knowledge is still a bit of a mystery as to why some people are so much more sensitive than others. Maybe a mystery that will get solved soon with all of the science that's unraveling. Okay, so those are the bioelectromagnetic fields that we are most commonly exposed to, that you talk about, and that's what you consider when you're talking about like the environment that we're in. Is there anything else from your perspective, like when you're describing how our biology interacts with the environment?
Yeah, absolutely. So actually what we do in our research team, and that's what I think it's even more fun, actually finding the conditions where the fields are actually doing a strong effect. I mean, effect which is robust.
Yeah.
That's what we are trying. That's actually what I'm most interested in. So what I would say, think so far, it's absolutely very important research field. We need to be clear to clarify the concern of the societies about these technologies. That's very clear. Now, honestly speaking, I think, but this is not my cup of coffee. I really like to find, this is how it looks like. There's like hundreds of scientists doing this research of the safety, and most of the things they are finding out, negative results means there is no effect. So it's actually good. But I would like to find the conditions at which electromagnetic fields do something to the biology and hopefully for benefit of the humankind. So that's what we are doing in our research team. So there, well, physically, the obvious ways to go is to deliver fields which are strong enough to do something with the molecular structure or cells. And that's actually a huge booming field. There is a lot of applications in what you would call the mainstream medicine. But particularly, for example, the so-called huge research field of the pulsed electric field, where the effects are non-thermal. So there is effectively no or very little heating, let's say, of the tissue or organism, but the biological effects are extremely strong. And that's what's being used in therapy, for example. I would say, most striking way, it is being used just to ablate the tissue. You want to remove parts of the tissue, but without heating or cooling it. It's called pulsed field ablation. It's a booming field especially in interventional cardiology. But then there are more subtle levels of this, because you can use also pulse electric fields to modulate biology without actually, it's not for the purpose of killing the cells, but actually to modulate their function. Because what we all know, and this is not disputed, it's also well accepted, that cells use electrical signaling. So basically we run on bioelectricity in terms of signaling. Of course, all goes hand in hand with the chemistry. So it's a very complex bioelectrochemistry, which is running our biology, energetics, and so on. This is something very well established. So this is actually, I would say, very interesting, how to modulate the, let's say, cellular scale and organism scale bioelectricity for regeneration and so on. For example, Mike Levine, you might know very well, a very famous professor for Tufts University, who is really an expert, I would say, visionary in bioelectricity, where he was able to show he can regenerate part of the lost, say, parts of the organisms just by reconstructing the real electric blueprint of the tissues. So this is actually a very fascinating field. So we are close to that, but going deeper to the subsolar and molecular scale.
Fascinating. Okay. This is such interesting stuff. And it's really heartening to hear about all of the research that's being done that could give us an alternative to just the sort of chemical model of treating illness. And as you also said, maintaining optimal health. That would be nice. Right. That would be good too. Okay, so getting back to the biophoton emissions. You mentioned for your thesis paper, you slept in a dark room and measured the light coming out of your body. Could you tell us how you did that?
Oh, it was so much fun. I was a bit younger. It was 20 years ago. And the first thing I would become immediately interested for some reason, I don't know really why, I was always interested, in internal processes in biochronology, so cycles of the biology. And my research question for my thesis was actually, I was so privileged I could coin it myself. I just came with the idea, and the supervisor said, "Okay, let's do that." It's very liberal supervisor. It was Professor Roland van Wyk. I had to really acknowledge him. He was so liberal.
Roland van Wyk?
Yes, exactly. Yeah,
he was your supervisor?
Right.
Okay. Yes. Our audience might know him as well. That's great. Okay.
So anyway, so my thesis was, the research question was, how does the biophoton emission from a human body varies over time? Particularly, I was targeting periods of few hours, or circadian rhythms, the daily rhythms. So my experiments were basically every hour or every second hour, I had to go to the dark room, and I was mostly measuring the standard spots, which are easily accessible, is the palms and dorsal parts of both hands. So
Okay.
and the fun started when I wanted to do it, 24 hours or 48 hours. So I was actually sleeping in a dark room. There was a bed. And a colleague of mine, she was so kind that she was waking up every 2 hours just to run the measurement, because the operation station was out of the dark room, just to know.
Okay. So did you have to put your hands on a machine? Or how was it?
Dark enough, and there was single channel detection at that time. We are now building something much more fancier and faster.
Okay.
At that time, was single channel detector which could be moved. So I had just put the hand under the detector. It was vertically, basically hanging from the ceiling, and I put my hand there. Measurement was run. Again, 3 minutes, and then other side, and I did it for, let's say, both hands, both sides, and then I fell back to the sleep. So that was quite fun to do that. So I collected a lot of interesting data, and I published it very early when I finished my master's. That was my first one of my first papers. So that is how I got to this field, and it's actually now it's really experiencing a new boom, I would say, this field. I can tell later on about what we are up to.
Okay. Yes. And so, what exactly are biophoton emissions? So, most people, myself included, were surprised to learn that our bodies are emitting light. It's like, what? We are? Most people don't know that. I learned that, quite recently. So, how is that possible? What is it? What's going on there?
So, of course, when you hear it for the first time, without any scientific background, or even having scientific background, you would get impression of something like aura-like stuff, something glowing around the body, which is known in philosophy since thousands of years, right? So, by the people who are experiencing could see some light around the body, and by what is measured by the technology, these are two different things, to my understanding.
Okay.
Because what biophotons, it's one of the terminology we prefer to call it biological autoluminescence or biological autochemiluminescence. I can explain details later. It comes from the nature of the phenomenon. This is the light which physically is being emitted directly from the object. So if you make a photo, you don't see any light around the object. It's directly coming from the object. So basically, the visual source, basically the light of sight, is really, you see, exactly copies the shape of the object. If you put the hand under the sensitive cameras, and the one of they have in our institute, you will see exactly the same shape of the light, with some interesting details, because there's some spatial properties. So light is not always completely homogeneous intensity. There are some spots which shine brighter than the others, may or may not. So it is a physical light. You are indeed detecting photons, so particles of light, in the range of what you would call visible range. But because there is so little of these photons, we cannot see them with naked eye. And I tried very hard, I can tell you. When I was still younger, I was sitting in a dark room for a lot of time, accommodating my eyes. You really cannot see that. Well, I could not. And most of the people, all the people who came there could not. We thought we can because we know where our limbs are. But then somebody else was sitting there, and you were asked, where is his or her hand? You cannot say. You have an impression, because you know where your arms are, but you can't really see this light.
So it's more we can more tell where it is through a spatial recognition, but the naked eye cannot see these emissions.
Yes.
And do you need I would imagine a very specific type of technical camera that's able to capture
You need very
them.
sensitive detectors to do that. However, they are not that unavailable. I will tell about it. We have a project which is supposed to democratize and spread this technology to the world, because
Really?
it's expensive. Yes, I will talk about it later. It's something I'm passionate about.
All right.
Once, say, a few months. So yes, so to go back to the answer. So it is a physical light emitted. So it's nothing, I would say, going out of the standard physics. Is really, we are perfectly sure, and it's not my opinion, there is a community which knows this phenomenon. So if you encounter a skeptic, they're saying this is not a true phenomenon, he is just not educated. So I was already having this discussion, and it's sometimes fun to see that some people are very smart by their education, just because it raises them something esoteric, they rather banish this idea completely without actually going to study what is out there in the literature, because there's a lot of data in the literature which shows this is really the emission in the visible range. So it's not just some thermal emission because of the fact that the bodies have certain emitters emit certain heat. This is really coming from as visible wavelengths.
Okay. So it's not, the light is not generated by heat. It is visible light that can be picked up if you have a sensitive enough instrument.
Exactly.
And yet it can be sometimes dismissed by people because it's a bit of not a far step into more esoteric
exactly.
ideas once you start talking about the body giving off light.
Right.
And then, because you did mention that you were inspired to take a scientific view to all of this by reading spiritual literature. So have those ideas come together for you? I understand that you are deeply rigorous in the scientific method, but also has that in any way informed your spiritual and philosophical views?
Actually, I thought about it for some time, and in certain years when I was young, it did. But now I kind of see it's different than I thought, and it's a development. So in a way, I can tell you my personal motivation in my life and in my research is really understanding of interaction, I would say, of the subtle fields and the matter, particularly biomatter. And then when I translate it to physics, it's interaction between electromagnetic fields and the materials, soft matter, biological matter. Because that's what something, is researchable. And we can think beyond the standard physics, metaphysics, but that's, much more difficult to work it. So I was a bit pragmatic, and I decided, okay, I want to do rigorous research. I want to use scientific methods to understand interaction between the fields and the biomatter. And this is very clear choice where you go. It's electromagnetic field because it's rather the subtlest you can get and still physically measurable. And, everybody using it, just using your phone. So it's something real. And everybody takes it for granted. So we can really study that quantitatively. Sometimes I like to make jokes about my surname. It's Cifra, which means in certain languages a number or a digit. And I make these jokes that I like to be quantitative.
Right. So, yes.
So answering that, there is, I would say, inner drive, my inner motivation is really deep. It goes beyond the rational. But what I really consider important is to keep the scientific methods. So to open up these phenomena to broader scientific community, because that's what I believe is my way how to make an impact.
Right. And where would you say things are at with that in terms of this work? And I'm going to use the word that you prefer over biophoton emission. You used biological autoluminescence.
Correct.
Okay. Where is biological autoluminescence in terms of the why, your lab is deeply focused on it, and you've mentioned there are many others. Where does it sort of fit into the wider field, and how does it relate to biophysics?
I like to take perspective of, as you mentioned, electromagnetic perspective of how the organisms work. So it's well established that from the cellular level, from even the simplest organism, there are membrane structures in the cells which use electricity to usually convert the energy or generate certain chemistry in it for the life. So it's, the electricity there from the smallest, let's say, units of life, the cells. And then higher organisms develop capability to harness electricity to make movements. So using musculoskeletal systems, and also for signaling, hence processing information. So all our neurology and electrophysiology related to higher brain functions. This all uses electricity. Now, I took your perspective of, let's say, physicists or engineers. So you can speak there of the frequencies or frequency bands. So this classical, well-accepted electrical activity in those cells and certain organs is reaching in frequencies usually up to few kilohertz of tens of the kilohertz. This means, thousands or tens of thousands of cycles per second. But in physics, we know that, there is much broader frequency range of the electromagnetic spectrum which exists there. So my supervisor here in Prague, Jiří Pokorny, he was really asking the question, so is there any biophysical activity in the cells which generates the much higher frequencies than those which are currently well known in the textbooks, and they are studied by a huge amount of people. So he was asking, for example, do cells generate microwaves? Do they emit microwaves not just because they are warm, but because there is certain activity which corresponds to these frequencies or fluctuations? And people have been asking, do cells and organisms emit different frequencies of electromagnetic field? And when you go like this through all the electromagnetic spectrum, you will end up also in the optical range, where we are speaking about emission of the light. So from this perspective, there is basically, I have one of the slides in my presentation where I show the spectrum, electromagnetic spectrum, and see this is well known, this is a little bit known, and there is a gap. So this bit known is exactly this biological autoluminescence. So when I took these perspectives, basically it's kind of what I call electromagnetic biophysics. Also, I sometimes tend to call myself, and when people ask about my profession, I say I'm electromagnetic biophysicist, basically combining biophysics from the electromagnetic perspective. And so this is how it fits the engineering and physical perspective. So there's different frequencies light uses. I mean, now really speaking about electromagnetic frequencies, light uses for its operation. And some of them are well described, some of them are not well described, some of them are unknown and maybe non-existent. We just don't have much data to actually say about something about that. So this is how it fits to, let's say, biophysics perspective, the phenomenon of biological autoluminescence. So it's just another frequencies which happen to be perceived by us as light. And yeah, fun fact is that any organism emits light because of it contains chemistry which is very general. It's oxidative chemistry which generates this light, by so-called excitations or chemically. So this is well established how phenomenon, let's say mechanism, how biological autoluminescence or biophotons is generated.
Okay. And so that's all living systems, not just humans that generate this light.
I should make a side note. It's important, actually, all organic systems, even the non-living. If there is you can just take a piece of butter or oil. When it's in the contact with the oxygen, or even when you seal the bottle, there is still some oxygen before it gets consumed. When the things gets really rancid, yellowish, let's say, the really natural butter sits, then it gets become yellowish after a long time. So this is oxidation. And this oxidation leads to emission of light as well. So it's all organic, basically materials when they are in contact with oxygen, especially some reactive forms of oxygen and other species. One of the reactions which is taking place also leading to emission of light. However, in the living systems, because these reactions are controlled, regulated, then also this light emission is regulated in a way. So this is what makes distinction between this light emission from non-living organic materials and living.
Okay. So the non-living materials are giving off light through an unregulated chemical reaction.
Correct, especially organic ones. If you take inorganic material, for example, metal, even the plastics is a bit organic, depends on what exactly it is. It's basically also material. Plastics are organic materials. So, but especially those which are typical for biology, those materials, if they're, let's say, if something which is of the biological origin, so to say, that's best example, can be any food, basically, even if it doesn't contain any more living cells, most of the good food does, it's still, even if it's non-living food, it still emits light just because it just, these chemical reactions are going on without any control. Actually, these can even emit much more light than a human. You just take a bit old olive oil, it shines more than a human does per the same surface area.
But it's the light is being created through a different mechanism in a human than in olive oil?
Oh, that's a good question. Actually, the fundamental reactions are very similar, but they are not regulated in the non-living systems, while they are regulated in the living systems.
So what do you mean by regulated?
So homeostasis, right? And dynamic balance of all different aspects of a procedure. So there is homeostasis in energetics. There is homeostasis in so-called oxidative stress. There is also good stress, so-called eustress from the Greek good. So eustress is also a good stress, and there is a balance of these stresses. And on this bioelectrochemical level, it's so-called reductive oxidative homeostasis, which is being balanced, so it's in favor of so the system stays alive. So, and this redox homeostasis, this I would say bioelectrochemical homeostasis, is the thing which is regulated, which then leads also to these photon emissions. So this is the, let's say, chemical perspective which of these photon emissions, which is well accepted in the community.
Okay. So that's why like the olive oil over time, that chemical reaction would cause it to go rancid, but we don't cause ourselves to go rancid.
Well, in the end, there is end of everything.
Or do we?
It's sad news, sorry. But yeah, we are trying to keep away from it as long as possible, right?
Right.
All the dirty things.
So have you found in your research that there are different levels of, I'm just going to make sure, of biological autoluminescence depending on a person's level of health or depending on their age or depending on where they live? Like, are there factors that change it?
Absolutely. This is actually the questions. I mean, it's actually many questions, right?
Yeah.
So there is quite some literature out there. As in our lab, we've been focusing really on understanding the molecular details of that. There's also recent reviews, which I sent some of the review papers. So when you go to the level of, let's say, the molecular and cellular, there are hundreds of papers which are explaining how light is generated at these levels of organization, let's say cellular and molecular. And there are hundreds of factors being explored, how they're affecting it. There is much less data when you go to the, say, organism scale. That means, plant, animal, or human scale. There is few tens of the papers, or maybe several tens of the papers. So there is still some data. So yes, let's stick to something which is most important to the audience, which are the people, right? So that's the humans. So what is known out there? So I just start to list as it comes to my mind. So as we age, we shine more. Our dominant hand tends to shine more. The extremities, so ends of the feet and hands, they tend to shine more than the flat surfaces. The nails, well, especially if you have no nail polish to block light, shine more. The people who are in the acute phase of some even mild respiratory disease, they shine more. People who are more stressed shine more. So long-term meditators typically shine less. And this is correlated by the level of the stress markers in the blood. So the higher the level of these different oxidative, or let's say generally speaking, stress markers in the blood, typically the higher emission is from the person. In a lot of diseases which cause certain asymmetries, this is extremely pronounced. So, for example, in paraplegic patients, how the body is basically paralyzed, that inactive one shines less. Physical exercise acutely increases the emission. Then there is also changes in for diabetic patients. This is a little more not clear which direction it goes, but because all of this is usually tied rather clearly to the physiology. There are some very, like, say, mysteries. Like, it's not clear why. For example, why nails shine more. It's not really clear why. But there are most of the stuff is tied to a physiology and to the biochemistry of the, let's say, underlying the human whole.
So the older you are, the more stressed you are, the sicker you are, the more light that you're emitting.
More light you are making. Yeah.
Why?
Because now this all perfectly fits to the standard, I would say, explanation of this phenomenon. And that's because there is more oxidative stress accumulated over time. When you are sick is increased. Well, there is some more things why when you are sick, but we can elaborate on that. So all it fits the paradigm of increased oxidative stress, which leads to increased rate of reactions, which generate this light. So this is how we understand it is.
Okay. So it's related to increased levels of oxidative stress. So could measuring, I'm going to keep looking at the paper you sent me so I say it properly. Could measuring the autoluminescence be a way to could that be a marker for health?
This is what we exactly plan to prove. So there is lens of the papers which bring some evidence to that. However, what we are trying to do in upcoming few years is actually massively expand this research.
Okay.
And I think now is the time to maybe to introduce what we are up to.
Yeah.
So we do believe, now this is still belief to be honest, right? We have some data to suggest, but it's still more to I would say, in large perspective, it's believed that the information which is carried by the signals can non-invasively report on health, particularly on both local and systemic oxidative stress index. That's something we want to build. So what we plan to do, and we are aware of the limitations, is the rigorous population study and massive statistics. Because what we are missing so far is have much more data on how this is related to age. There's only one paper on it, maybe two, on a few tens of the people. How this is related to lifestyle, particularly a whole style, let's say, typical nutrition the person has, the skin type. There are particular diseases also are affecting peripheral blood flow. This is all affecting it. So what we need to build, and that's our grand, I would say, plan for upcoming 10 to 15 years, is to build our global human biophoton atlas, as we call it. And we are just unleashing that.
That sounds really cool. Could you say that again?
Yes. We are going to build global human biophoton atlas.
A global human biophoton atlas. Love it. I love it. Okay. Sorry. Keep going.
Now we are about maybe the third person out of our institute who hears that. So we are just ramping up, preparing all the branding, all the fun part of it, because we want also to gamify that. The goal is in our first 2-3 years, we're going to do a pilot study at the institute. Well, we can bring on volunteers if you come over. We will have some bloggers coming already in April, just to be on site and try it, with our hands physically.
Okay, cool. So you're saying if people are interested, they can come to Prague.
Absolutely.
All right, like Roderick Lambert did, how I met you.
Exactly.
He came in.
But this is bigger. This is bigger because beyond when we finish this pilot, we'll be building a network. Thanks to you, we are already doing it, right? In this discussion, we want to build a worldwide network of ambassadors, and we will provide them as much as affordably as we can our systems, because we are building on our own. So we know all the technology, we can scale it, we can produce tens of hundreds of these systems. And we want to make, imagine we're going to have a website with the globe and the spots where you can go to measure your biophoton emission. It will be fun and great.
So fun. That's so fun.
One of my missions along this line is to really get this to textbooks. So everybody will know, who gets some, education that, in the school, we might learn in biology that, heart uses electricity, brain uses electricity. So we should learn that, organisms emit light, all of them, not only few, which we can see by naked eye. So this is the plan, and the idea is there is science idea behind that. If you increase the number of the people in the database, then you are making all the knowledge much more precise because you're increasing statistical significance.
Yeah.
This is how typically works when there are sort of phenomena which you want and the effect size is not that strong. You need to increase number of the n of the samples or subjects to get that. So this is idea, and we want to make it big. So the idea is that first few years, the few hundreds. I would love that within 5 to 7 years we go to 10,000, and my ultimate goal within 15 years, let's say till the end of my career, to have 1 million subjects measured all over the world using the ambassador network and leveraging all the enthusiasm from the community, because we will need people and of course very good logistics which we can support, but we will need a global engagement in this.
That's really fun and super exciting. And I love the way you're looking at it. It's like, yes, we can measure the body's electrical output, and we've done so in lots of different ways, and it's taught and people understand that. And so now the next step is for everyone to understand that our body emits light to that same extent. Okay, so let's talk about the Global Biophoton Atlas. So would your vision be that the machines or the cameras, what do you call them, that would measure it?
Systems which are easy to scale are the photodetectors. There are particular types of them.
Okay.
We plan to use photomultiplier modules, which are very robust. You can bring them out to the lab. They operate perfectly and reliably for a long time. So basically, those enable the operator to basically measure the overall light from a certain part. Usually, it's how it looks. The system which we want to spread to the world is a small black box which you can just transport anywhere like, and the detector. So what you get there is the basically amount of light. You don't see images. You see numbers, but you can put them to a certain perspective. After getting some data, you can say, yeah, hey, the point is that we're gonna measure these light signals, like basically the amount of light you emit from certain areas which are accessible mostly has, and we have to, and what's very important for it, we'll have a questionnaire. We'll have to write all the consent because I think this is a medically approved study, and based on this, we're gonna build a database which will be all the data will be open, and all the ambassadors and collaborators will feed it because we plan to have standardized procedures so it's comparable, and this will bring a lot of information. And the questionnaire is very important because this will basically, we have twice, we are going to put there questions, we will put you to the scale. So for example, for this age, for this gender, for this, lifestyle, where you are, do you shine too much or too little, it's, the number itself doesn't mean much without the context. And with this, we're going to collect the information about the context and the light information itself, so amount of light which one person emits.
That's really cool. So who is best set up to host this technology, or to become a center for measuring the emissions? Would it need to be a hospital? Could it be a clinic of some kind?
So we want to keep it open to basically anyone who is willing to follow the protocols, because there is a science behind
it.
Of course, in your free time, you can play with that. That's the fun part. But we want something back from that, and that's the data, right?
Yeah.
So this is still very early. First, in the first few years, we're gonna have approval for a single center study. Going multi-center study is possible, but there will be some. I think since I believe it will be possible, and it shouldn't be limited to clinics or hospitals. It can be health coaches, consultants, longevity clinics.
Great.
Anyone who is interested, what we will require is that it pays back in the data. So once you get a device, for example, rented or for any conditions we'll agree on, we just want you to use it to collect as much data according to a protocol, and that's how we plan to do that. So we will be open even to enthusiasts, as like if you make a deal over the conditions, we can think of providing that. So it will help us to build a science about it.
So cool. All right, everybody listening, we have many practitioners in our audience. If you would like to be a biophoton emission measurer, stay tuned. Ambassador. I know, I like to play with words. Yes, ambassador, stay tuned. You will have that opportunity coming soon. Okay, so we talked about biophoton or bioluminescence emission as a marker for health. Is there anything else related to health that you have even theoretically thought about? Like, is this our ability to create this light doing something for us, or our ability to regulate it? Because if the difference between non-living and living systems is that we can regulate it, and then when we're older or unhealthy, the light goes up, does that mean our capacity to regulate has been diminished in addition to the oxidative stress?
Right. That's how it works on cell level, indeed.
Okay.
Yeah.
So what does it mean to our biology to be able to create and regulate this light? Like, what are the...
So the ability to control the underlying processes is crucial for health. So we believe it will be a marker of biological age at a certain point.
Okay.
So not the chronological, but the biological one. So that's it's I believe it's tightly coupled to these to the oxidative stress and oxidative, let's say, redox homeostasis or reductive oxidative homeostasis. So definitely the capability of organism to regulate the processes which lead to this light emission is very crucial and fundamental for biology. Now, there is one branch which I was always fascinated about. It'll be super speculative, and you might like to heard about it.
Of course I would.
It's like
I love the speculative.
We go beyond, let's say, the established science, because that's also fun.
Talking theory now, people. We're talking theory. All right. Love it.
Not theory.
Not theory. Okay. It's not a theory yet. It's still a speculation.
Experiments.
Okay. All right. Sorry. I
know,
know. I hear from
theory-
people when I play with words. They're like, you didn't.
No problem. And it's just,
No, it's
terminology-wise,
good. Keep it going. Okay. So we're talking speculative. We're not even
speculative
into
interpretations.
the theory yet. All right.
So,
Got it.
Okay, so just terminology-wise. So when you say theory, that's something which is some formulations, often quantitative, when it's in physics or biophysics or even engineering, which predicts something which you can experimentally test. That means theory.
Okay.
So it's
So what you're
speaking,
about to tell us, we're not even at that stage yet. We're pre-theory.
actually, what I'm thinking about is about experiments which are
Okay.
very fascinating, but are hard to reproduce.
Okay.
This is actually where the most of the fun is. When you do see something in experiment, a real thing, but then, and somebody else tries to do it as well, but he's not getting the same stuff.
Right.
And this kind of stuff is very fascinating, because in these kind of experiments, which we call they are not easily reproducible or irreproducible, this is like a gray zone of science. So there is something there. It is either just artifact that something was done wrong, so we got the interesting data, but we don't know what got wrong, or it's actually really true thing which we got, but the other one who tried to reproduce couldn't reproduce because it didn't do the stuff exactly as she should, or he or she should. So now this fun part, and this is about the, I would say, speculative suggestions that biology could use this light to communicate. So there are quite a lot of experiments on this kind of guide, that you have say two cell cultures which are separated mechanically. So let's say there is a flask or a dish with a cell culture here and here. And now you stress one, and then, as we know, as you stress, the cell culture will start to shine typically. Now the fun part is that some works claim that some papers claim in there, and there is usually, well, some of them quite reasonable research. You don't see anything wrong methodically there. Some of the papers claim that the other culture could respond just by seeing this light from the other culture. So it means if as if some experiments suggest that the biology could use this light for communication. This is absolutely fascinating, right?
Yeah.
But there are many buts. And I'm one of the authors who are telling what are those. And I like to play with these ideas. We tried on our own, and it's super hard. Sometimes it just doesn't work. So you cannot rely on that. So it goes beyond science sometimes, because if something isn't reproducible, it's like, would like to have a car which starts only every third time. So one day it doesn't start at all, another day it does. It's useless. It's not a car, really. I mean, it just starts randomly. So what can you make of it? So these kind of experiments are super difficult to work with, because then you just suddenly, for some even long period of time, they just don't do the stuff which they used to do before, and they just don't know why is it so. There are many speculations why it could be so, why it only works sometimes, or for some people it doesn't work at all, never. So this is fun, but this is exactly this how these kind of experiments tend to behave. But this is in core very fascinating, and I guess for obvious reasons, right? There are claims there could be communication channels using lights, but there are many buts, right? Because this light is so extremely weak, so it's very hard to imagine how it could work in let's say normal light conditions. So most of the experiments are being done in dark, and one could say, yeah, it's dark inside of our bodies. Yes or no? That depends. So yeah, if the cells talk to each other using light language, it could be fun, but it's still, I would say, a very open question. So this is the fun part.
Yes, this is really fun. Okay, so you have the experiment is you have cell cultures in two separate petri dishes. You trigger one of them to have a stress response, which increases its light emission. And then you look to see if that light emission is received or changed in the other. And sometimes there is an observable effect, and sometimes there isn't. Is that sort of what's going on?
True.
So it's like the
Totally
effect is
exact.
there and it's real, but without understanding how to reliably reproduce it, no one wants to commit to the.
And there is this uncertainty, because you can remember, in every work there's always uncertainty. So even by a random, playing dice, how probably is that you will throw 10 times in a row? Very low, but it's possible, right? In the same way, you can get some effect without actually being reproducible. I mean, I would say really in a way that it's common. So some things can be just obtained by randomness. You can get some reading which is beyond the threshold saying, yes, this is an effect, just by chance. And because of the publication bias, that means that if things don't work, usually published. That's the problem of the academic research. Not only academic research, anyone. People like to be positive, right? It's human nature that you want to, I achieve something. It's very rare to publish, hey, this just didn't work. And because of this bias, probably most of the negative results are not even published. So we don't know even what went wrong in those experiments,
Right.
what they tried and why it didn't work. So
Right.
the ratio of, if these things worked, usually people publish that, but there might be hundreds of other papers or works which have never been published, and they just saw there is no effect. And this is because this change is real. This is like this publication bias is there. That's why we are so careful to say this is really true effect. Although there are a few tens of papers which have these findings, as I mentioned. So, and this is a very tricky area of research. I know people who ruin their careers trying to do that, because just for several years there are no results, no funding, out of the business. And doing good research just takes time and money, because you need to eat, right?
Yep.
Pay rent and other stuff. So this is very difficult. There are some extreme cases from former Soviet Union that, there was academic research like, just do whatever you do, just pay a little, you just survive and do the stuff. So there was some researchers might know that. And I learned Russian just because of these crazy things. There are works from Kaznachev who worked on this 30 years, and they were doing these kind of experiments of stressing one culture and looking another for many years every day. And they found, this is crazy. I remember still the graph there, the Russian description. They found cycles over time when these experiments tended to work, and the effect faded away completely. And it changed over time, periodically over the year. I don't know
So
what
it was linked somehow. There was a cycle to it.
there was a cycle to it.
It wasn't random.
But how can possibly in our research system you could do these experiments? They were doing 30 years these things. We have funding now for 2-3 years.
Yes. So they stayed at it for 30 years and they were able to discern a pattern.
Exactly. But they have to do it every day or every week, a few times at least, to see this pattern. So I don't know how I can trust this data.
As a side note, I love scientists. Like who goes and does the same experiment every day for 30 years? Like
Scientists,
God bless him. That's amazing. Okay.
you have to be really freak to do that, right? So
Yeah, I mean, you just have to be so committed and so focused and motivated to find out what's going to happen. I mean, it's amazing to me. But that's also a really good point because all of the people throwing out or not publishing because it didn't work, like that's still useful information, is what the Russians showed.
yeah, that was still Soviet times. They were somewhere very far in the east. Well, yeah.
Isn't that
But
something?
this is like
Okay.
bigger problem. It's not only about this research field.
Yes,
Any
yes.
research field has
Yes.
huge positive publication bias.
Yes.
You don't see
course.
negative data which stays in drawers for different reasons. Yeah. So
Yeah,
anyway,
no,
so
of course. And that does make sense. But in an ideal world where it was, like those Russians were almost operating in an ideal world where they weren't tied to funding and approvals. They were
you would
just
like to live in that world, but if you are
that's true.
trained scientist, probably you would like you could do this.
But I guess I'm thinking, like in an ideal scientific setting, there wouldn't be these kinds of constraints. You could just follow
Yeah.
your, in some sense, maybe your gut feeling that there's something there, even if in the short term you're getting mixed results or things that can't be reproduced or things that seem random.
But again, since it was only single lab who was doing these crazy things, because it's just, I can't imagine who else could be doing that, for such a long time.
Yeah, no.
There is nothing to compare with like this. There are some other long-term studies with some other cycles, but it's very different fields. So could it be that they have certain periodic artifact in their setup over the years? We don't know. Could there be that over the time they had increased moisture in the lab, which they definitely had? It was no fancy lab which you constant moisture and temperature, and they have leakage during a certain time of the year? I don't know. So it's fascinating, but we have to be very cautious about this. Typically there's a saying, if there is extraordinary data requires extraordinary evidence. So it to be really strongly, very convincingly. So this is exactly the type of the field. Having very strong claims about these kind of things, which are rather unexpected based on, let's say, what physics and biophysics knows, have very strong evidence to make strong claims. If I'm really trying to be careful with the words.
Okay. So if the idea that cells can communicate with each other via light is unexpected and not accepted, what would need to be true in order for that to be
I think
a likely scenario?
One of the papers I sent you, it was already in my more skeptical years. It's we call it
the one about how there's only a ghost of a chance.
Exactly, that one. Yeah.
Okay.
There we exactly list what are the problems, why it seems to be not, well, why it's hard to accept by any reasonable biophysicist, I would say, because there are certain, just simplest idea, simplest thing, which is, just to give you an example. I was thinking about it today, how to put it clearly. So this light is extremely weak. Imagine a lighter or a candle light. Now, take this candle light and let it light to International Space Station, so 400 kilometers above the ground level. So imagine you're trying to look on that from you're somewhere in darkness, completely looking on the space station. Sometimes you can see that, right? It's one of the satellites flying around. And there in that space station, they light up the candle. And the amount of light which comes from the candle down to the ground is the intensity of the light which humans and organisms emit. Is this so weak as a candlelight?
Okay. The light emissions from our bodies, as to compare metaphorically, would be like seeing candlelight that was up in space.
numerically it fits. I was doing the calculation, so that's what it
Okay.
comes.
Of course you are. Okay.
I'm Cifra, right? So
Right.
the digit.
The digits. Get the numbers. All right. So the visibility is very weak. But is there still something left they could be communicating?
In principle, yes. But the problem is here then the noise. Everything, all other signals that organisms integrating are can be much stronger, like many orders of magnitude, millions, billions times stronger than this. Other, let's say, chemical signals. So this is the major conceptual or paradigm challenge to overcome. And this is exactly what we write in the paper. There are limitations and there would need to be extraordinary things happening in biology which we haven't noticed so far, which could enable these deciphering these very weak signals from the background of all other stuff. And this is super hard to understand because the way out of it, and there are of course people try to find about it theoretically, if there is certain coding, certain patterns in time and other stuff, or space-facing wavelengths. People were thinking of all possibilities that you can physically think of because people are very good in coding, and cryptography, and all the stuff is very advanced. So there were some ideas how to overcome these problems of very low signals and high, let's say, levels of noise which organisms perceive. It's very tricky. It's very tricky. It's all the possibilities seems to be unlikely so far, unless you assume something very extraordinary happening in biology, which is not proved so far.
So what would a paradigm look like where this made sense? The light communication between cells made sense. Like
So yeah.
just as a full speculation.
So one of the things you mentioned, there would need to be extremely sensitive integrating and decoding detector inside the cells, and it's not clear what it could be. We don't know. We just don't see anything in the cell which could it be. This is basically it. I mean, technically, it's possible to take the candlelight from the orbit, from the space station, but you would need to look on it a very long time, very sensitive detector, and there are some tricks how to do that. There need to be blinking light, and you know exactly you would need to know the code, so to say. And yet you have to be extremely sensitive. So there is no clear idea what could be decoding any code, if there is any code in these light signals. And I can tell you we're trying very hard. We have a few papers on that. This is not very essential because they're very mathematical. What could be the code in these signals? So we couldn't find any except very one weak signature. And then there's one side that's on the sender, and on the receiver side, there will need to be something which can decode that in the huge amount of background signal. So we would need to have these. We need to prove there is certain code inside this specific sequence, or very broadly speaking, it's not like sequence in time. It's very complex in a complex space of the properties of the light, even from quantum perspective. And on the other side, on the receiving side, if I simplify it, because it's it can be more complex. It's not when you go to more.
Yeah, please simplify. We'll take the simplified version.
But I think this is important now because I'm simplifying the concept to sender and receiver. But now, if we like the landverse from quantum biology, it can be just sharing as a field does, right?
Yes.
I'm simplifying the words just sender and receiver, but it can be more complex. But this is
Right.
already a much
Okay.
more crazier idea, which is known from quantum biology. What is not really much known, that cells could be somehow entangled or field coupled. I mean, this is because the field is not just the particle. It's it can be interfering and coupling the things together. So it's not like simply saying things go there and there, because it's all around and mingling, so to say. So
Yeah, I guess that was kind of what I was wondering, if there was more that at play than there's the biology, but also the field around the biology. Is there some medium through which they could be communicating that we don't see?
well, this is all philosophy, right? You can think of whatever, but then it goes pretty much beyond the standard science. There are a lot of weird things which I think I don't know if they're worthy to speak about because they go really beyond my expertise. You can find a society which are dealing with this. They are definitely not, I would say, following the standard science for different reasons. So, for example, there is well-known in US established Society for Scientific Exploration. You can check. They're very extravagant topics, so to say.
I love it.
Yeah, but
Okay.
that's different. That's not my field. I just know
Right.
they exist. They do all the crazy things you can imagine, from remote viewing, telepathy, and this stuff. But that's not it's not my cup of coffee for my research. It's fun to hear
Yeah.
about it, but for me, it's I can't really use it in our research.
Right. And that's fair. And I think, obviously we need to stay very grounded in what we can figure out for sure. So appreciate that you're doing that. And so to wrap up, could you just say, if your if your wildest dreams come true and you get to have, a million different data points on the bioluminescence emissions, what would what would you maybe expect to see or hope to see in that data? What would be like really cool to
So I would hope to see
know?
surprises. I would like to see the things which we didn't know.
Good
What I
answer.
expect to see, though, is that if everything is well controlled, we will be able to monitor, as I mentioned, through these indices of oxidative stress to probe, let's say, effective biological age, to see effects of therapies, different kinds of them. Because what will be interesting to see longitudinal evolution, like if you measure something in one subject and then over time, after certain interventions, this could be interesting metric. Just purely pragmatically, it's completely non-invasive. You just watch. You don't even send any light. You just watch the light being emitted from the organism. So it's completely non-invasive. So no burden for the patient. You just matter of minutes to get the signals. So just from this perspective of being completely non-invasive, that's something that I believe is just cool. If it brings enough interesting information, but that we will know. So yeah, so on this pragmatic level, having new biomedical technology which can non-invasively tell the level of the, say, biological stress, I think also be useful in different medical fields to monitor different interventions, medical interventions or different interventions in health. That could be useful. Now having this huge database, we can now then nicely compare, okay, so this worked. So we do see change in this metric, let's say this oxidative stress. And of course, also, frankly speaking, as my, let's say, personal research mission is really understanding of interaction within the field and matter. One of the important side effects will be increasing the awareness of this. I think it really inspire many people, many new scientists to think about more broadly about the bioelectromagnetic phenomenon. And I think that's maybe in the end the more important for this project. If we call it Biophoton IQ or Biophotonic project. So that will be my biggest dream, that really everybody in the world knows that organisms emit light, and start from that thinking further.
I love it. I'm so excited. And congratulations to you and your team for coming up with this idea and moving forward with it and, constructing it in a way that can involve truly anyone who's committed and interested. That is, I think, really exciting information. And I know our crowd is going to be excited to participate and to follow along and to keep learning more. So, is there anywhere where people should connect or with you or follow you if they want to maintain updates?
I'm active on 8 social networks, but my primary one is LinkedIn.
Okay.
It's the professional network. As I mentioned, this project is not online yet. We like to assume we're gonna have first public presentation, if it all works out, in Washington D.C. in the Quantum Biology Forum. It's still not accepted abstract, but I believe organizers will accept that. I think
Okay.
that will be first public thing, and by April, hopefully we should have a website online, and we'll start to build a network of interested people. After the pilot study, we'll try to make it as fast as possible. And when we see promising data, we'll step up beyond the, let's say, the Prague and go worldwide. And of course, people will be very much interested. It will be even interesting to purchase the device. We can make it faster because of, the funding will be bottleneck for a certain time, but we'll have to see how we'll scale it. We have different strategies how to do that, but we'll see depending on it's a number of interested people and how committed they can be to deliver the data.
But there is a device that they could rent or purchase that will be able to. This is so cool because it must be very difficult right now because when you look for photos online, there aren't very many, which led me to believe it's quite hard to get to take them. So you're changing that.
Yeah. So again, this will be not making photos. It'll be collecting. That's
the numbers,
possible.
Right?
It'll be.
But
just
could you then
create
images out of the numbers?
Very very coarse images. If you like, imagine like a scanning detector. So just light. You could basically scan and then reconstruct, but it's very clunky.
Okay. So it's important clarification. So it's not a photo. It's you're picking up the data points and storing it numerically inside the device.
Yes.
So people can track the levels of emissions over time as someone recovers or ages or gets ill, or if there was a change after a lifestyle change or a certain intervention, you can measure if there was a change. So exciting. So exciting. Thank you so much, Michal.
Very shared excited because I think it will be really big and impactful in a positive way.
I think so. Thank you. Thank you for coming up with it.
Thank you, Meredith.
Thank you for your time today. And I look forward to doing this again when we can hear some updates.
I will be happy to those. Thank you very much.
This has been the Quantum Biology Collective podcast. To find a practitioner who practices from this point of view, visit our directory at quantumbiologycollective.org. If you are a practitioner, definitely take a look at the Applied Quantum Biology Certification, a 6-week study of the science of the new human health paradigm and its practical application with your patients and clients. We also love to feature graduates of the program on this very podcast. Until next time, the QBC.